So we've established the kinematics for rotational motion. Now we're going to switch over to an energy perspective and talk about some things that we can do. So suppose that we have this object. We have two large masses connected by basically massless rods. So the whole thing creates one continuous object, and this is going to rotate around the axis of rotation, which is right here, into the screen. So it's rotating like that. There's a new quantity that we could talk about. Well, we want to get to energy, so we're going to head to kinetic energy. And so to begin, what we want to do is find the tangential velocity for each of these masses. We're referring to point masses, we would call these. So this is a point mass analysis. Masses. And so the tangential velocity from last time is going to be the angular velocity times the radius, how far away it is. So the velocity for mass 1 would be the angular velocity of 1 times r1. And the velocity of 2 would be angular velocity 2 times r2. So for kinetic energy, remember that kinetic energy, say of 1, is going to be 1/2 m1 v1 squared. Likewise over here. Kinetic energy 1/2 m2 v2 squared. And now we can substitute. So we can substitute this quantity in there. And what we'll get is that the kinetic energy of each item, each object, is going to be 1/2 m1 omega 1 squared r1 squared. And we get the same over here. m2 omega 2 squared r2 squared. Okay, but the thing that we have to keep in mind is that these two quantities are the same. So omega 1 equals omega 2. These things are going to move with the same angular velocity. They have different tangential velocities, but the same angular velocity. And what we want to know is the total kinetic energy of the entire thing. So the total. So the total kinetic energy is going to be 1/2 m1. I'm just going to put omega squared r1 squared. So it's just the angular velocity of the entire apparatus plus the kinetic energy of the second object. 1/2 m2 omega squared r2 squared. Okay, so we have some common stuff. We have 1/2 in common, and we have that omega squared in common. So let's rewrite. We're just going to rearrange. Total is going to be 1/2. Each of these have 1/2 times m1 r1 squared plus m2 r2 squared. And then we would pull out the omega squared to the other side. So the total kinetic energy is going to be 1/2. Now, if I had 5, 6, 7, 8, 9 objects, I could use the same equation. So this is just the sum. So we're going to do the sum for I of mi ri squared, those are i's, times omega squared. So this is the total kinetic energy for a system of point masses. And this quantity in parentheses, this right here, that is the moment of inertia. And we use a capital I for that. So I'm going to rewrite. So the kinetic energy, I'll talk a bit more about the moment of inertia in just a second. The kinetic energy for point masses is going to be 1/2 I omega squared, where I is equal to the sum of the masses times the distance from the axis of rotation. Put an I on there. On your equation sheet, you have this one. You have these two. Now, this is only for point masses. And you can see that it depends on the distribution of the mass. Of masses about axis of rotation. What does that mean, though? So let's go back to our picture. So we kind of know what inertia is from our study of Newton's laws, and that's just a resistance to acceleration. So it's the same thing here for rotational motion. That the rotational inertia, it's a resistance to change in angular velocity. So things that have really high rotational inertia are hard to rotate. Or if they're already rotating, they're hard to stop. And the opposite. If it has low rotational inertia, it's easy to spin and it's easy to stop. And so it all just depends on where the mass is distributed. And notice it's dependent upon the square of the radius of where it is. So that has a bigger effect than the mass. So let's look at like two examples. Say we had an axis of rotation, a vertical axis of rotation. We had two objects. Or we had like a beam that we want to spin. So we're going to look at two different ways of distributing it. So if I took, say, 1 kilogram masses like this, and I put them very close to the center, then this is going to be easier to spin than if I were to put them way out on the edge. We'll do this demo in class. You may remember this. I have this set up with meter sticks. So if they're very close, you can see that the R here is very small for both of these. R is going out this way. So this is going to be easy to rotate about that axis. Whereas this one has a really big R, so it's going to be much more difficult to get moving. Or once it's moving, it's hard to stop. So that's what we talk about with rotational inertia, is just the resistance to a change in its angular velocity. And we define it for point masses to just be that, the sum of the mr squareds. That's for point masses. So let's do an example and then I'll come back and we'll redefine this for non-point masses. Okay, let's look at this. So suppose we have three masses connected with massless rods. So we don't care about these rods, it's just these three masses. And we're going to look at the moment of inertia, or rather the kinetic energy, for a couple different situations. So the first one, let's say that the axis of rotation goes through mass 1, coming out of the page. So this thing will rotate like this. So what we want to do is we want to find the kinetic energy for the system, which would be 1/2 the moment of inertia times the angular velocity squared. I guess we should give it some angular velocity. Yeah, well, whatever. I'm just going to do it algebraically. So the moment of inertia for point masses is going to be the sum of mr squareds. So that's what we'll use here. And keep in mind, this is for point masses. It only applies for point masses. If it's not a point mass, you can't do it. So we get the sum of all of the masses times the distance squared. Mass 1 is on the axis of rotation, so this one doesn't contribute because this one's going to be stationary. Everything else is rotating around it. So all we care about are these two over here. So it'd be mass 2 times the distance from the axis of rotation, which is this distance right here, the 0.4. So times 0.4 squared plus mass 3 times the distance here, 0.5 squared. And then we'll take that whole quantity and multiply by omega squared. So whatever that is. And that would tell me the kinetic energy. I'm not going to finish this. The important thing is just to keep in mind, you have to draw the situation and think about what's included and what's not. So B. So now suppose, let's change color. So B. Now let's run an axis of rotation through these two masses vertically. So now this thing's going to rotate like this, out of the page and then back into the page. So what you should see is that these two masses don't contribute to the rotational inertia. It's only this one way out here. So the kinetic energy in that case is going to be 1/2 of this one, mass 1, times the distance, 0.4 squared, and that's your rotational inertia, times omega squared. That's it. Okay, so now what happens when they're not point masses? So now we're talking about uniform rigid objects. We still have to be able to deal with it. So I'm talking about like a rod, so a cylinder, which is rotating about an axis, say at its end. So the kinetic energy of this thing, it's still going to be 1/2 I omega squared. Let me draw. So it's kind of moving like that. That's your omega. So it's this quantity though. So if we think about it, we can't really do a point mass. And one thing that people try to do is just think of like center of mass, and that does not work. So imagine that we just cut off a little piece of mass here. So this one right here, you can see the distribution, and this one over here. So we'll take two equal masses, and you see how this distance over here is much greater than this distance. And remember that the inertia is proportional to the square of the radius. So just by finding the center of mass, that does not work. We can't find the center of mass. Instead, what we have to do is we have to take like these little tiny pieces of mass, we'll call them, say, dm, a little sliver of mass, and then we have some r, some distance it is. And so the kinetic energy, or rather, we'll just do the inertia. The inertia in this case, we're going to see is some integration. And so it's going to be the integral of the dm times r squared. I should have written it the other way. So r squared times m. So we'll take the integral as we move, as we go across it. We'll get into more calculations for this. So this is your rotational inertia for uniform objects. Most of these are going to be given to you, uniform rigid objects. There's two that you have to know the derivation for, and that's a rod and a sphere. You have to be able to deal with. But let me find a little chart for you. So here are some common equations for different rotational inertias. So here's the rod. It depends on where the axis of rotation is. So you can see a rod rotating about the end, it's 1/3 m times the length of the rod squared. So that's your rotational inertia. And you don't have to integrate this. You just use this directly in the kinetic energy. If it's in the middle of the rod, then it's 1/12 ml and so on. This one is it's a hollow ring, mr squared, and then you get 1/2 mr squared. You can see that they all have this like mr squared. It's just that the factor over here is what changes. And we'll talk more about this. We'll do some calculations and we'll go through the derivation for the ones that you need to know. Let's do some more examples using this now. Okay, so here's our setup. We have a solid cylinder which is connected to an axis through the center of it. And so it's a big drum. And then we wrap a cable around it, and then the cable comes off, and then we're gonna pull with a force of 9 newtons for a distance of 2 meters. So we're gonna grab this and then we start pulling it. We pull it for 2 meters, and we wanna know what's the angular speed of the drum and what's the speed of the cable after it's gone that 2 meters over at this point. We're given some quantities. The mass of the drum is 50 kilograms and the diameter of the drum is 0.120 meters. And then we also are given the rotational inertia for a solid cylinder with the axis through the center, and that's 1/2 mr squared. So now we can start working with this. So what we'll do is we'll take an energy perspective, because we're gonna have some acceleration of this object and stuff. So basically we have a force and we have a distance, and so that lets us know that there's some work being done. Oops, getting used to writing omegas. So the work would be the force, not P, it would be the force times the distance. Because this is we're assuming it's a constant force over that distance. And so that would just be 9 times 2. So we get 9 times the 2 meters, so we get 18 joules of work. So all of that work is going to go into, we're assuming everything's frictionless inside of it. So all that work is going to go into the kinetic energy of this rotating drum. So we have that the work is equal to the kinetic energy of the drum. So the work is equal to 1/2 rotational inertia times omega squared. And this is what we want to find. We want to find that rotational velocity, the angular velocity. So we multiply by 2, so it'd be 2w, and then divided by I, and then take the square root. And that would be your final angular velocity. Now the I is this quantity here, so we might be able to simplify this. So that'd be 2, that's work. Don't get confused. I start writing everything. 2 times the work over 1/2 mr squared. And we'll take the square root of that. That would be your final angular. 2 divided by 1/2 is 4. So we get 4 times the work over mr squared, and the root of that. And I'm just going to stop there. Now root, you could go on, because that would be take out a 2 over r. So 2 over r times the square root of work. The 18, when I say work, I'm referring back to that. That would be 18. Everything else you just plug in. So that would tell you your final angular velocity. To get the speed of the cable, well, the cable is out on the outer edge. So basically you just find the tangential velocity here. If we find VT, then we would know the speed of the cable, since it's not stretching. So the speed of the cable would be the velocity, which would be omega times r. R is 1/2 of the diameter. So it would be this quantity times 0.06 or 0.6. Which one? 0.06. Anyway, that's how this is how you're going to approach it. So when we're dealing with energy, we'll go back to our work energy principle. Let's do another one. Okay, here's the last example and then a quick just comment on gravitational potential energy. But suppose we have an unknown disk-like object, but it's not a disk, so we can't find the moment of inertia from the equation. And we want to know what the moment of inertia is for this thing. So the question is, what's I? And so it's attached to a wall, and then what we do is we can wrap a string around it and then hang a mass off of it, which is some height above the ground. And then basically release this thing, and then we'll make some measurements and we can figure out exactly what this moment of inertia is. I'm not going to put any quantities, we're just going to work through it. But the idea here is that initially, again, working with energy, we have some gravitational potential stored in this thing. So we're going to have some gravitational potential in the little mass, I'll put a little m. And then that's the only thing. And then afterwards, so right as it's about to hit the ground, we would have kinetic energy in the little mass and kinetic energy in the disk. So that would be our setup. And so then we can figure out we want to know the moment of inertia. So the potential energy of this hanging mass is going to be mgh. And then the kinetic energy of the mass right before it strikes the ground is going to be 1/2 mv squared plus the kinetic energy of the disk, which would be 1/2 I omega squared. All right. From this point, now we can solve for I. So I'd probably multiply everything by 2 first. So 2 mgh. And that's going to cancel on the other side. So we get mv squared plus I omega squared. So we can move this over. So 2 mgh minus mv squared. That would leave this term, and then we divide by omega squared equals the rotational inertia. Now, if we were doing this, we probably wouldn't want to measure both of these quantities, but we can redefine this one in terms of that one. So the velocity is referring to the speed of the mass right before it strikes the ground. But that coincides to the speed of the rope along the edge of this thing. This is big, or we'll just put a little r. So it's the speed of the rope along the edge is the same as the speed of the block falling. So we can redefine this because remember that the tangential is omega times r. So it's v over r. So we get 2 mgh minus mv squared over v squared over r squared is equal to the inertia. Multiplying that up, you get 2 mgh minus mv squared, that quantity times r squared divided by v squared. That would be your rotational inertia for this object. So all you would need to measure would be the mass, the height, and then the velocity of the block as it's hitting the ground. And that would be it. That would plug it in, and that tells you your rotational inertia. And then from there you can figure out other things like how fast was it spinning around. But that's your energy approach. Okay, the last thing to keep in mind is that in this case we're ignoring gravitational potential energy of this disk. And so gravitational potential the gravitational potential U G is going to be the mass of the object times G times the vertical center of mass, the vertical position of the center of mass. In your homework assignments, you probably have some problems like this, and this will come more into play when we start dealing with statics. But if you had like a rod and you're going to release this thing, then you'd have to think about the gravitational potential. So you need to find the center of mass, and then you would want the vertical position of that thing. Sorry, from here. So that would be your Y center of mass. And that's it. So that's it for all of this. We will, next time we're going to do the parallel axis theorem, which allows us to deal with objects when the axis of rotation is not where we want it to be. But that's it for now.